Welcome to our second day on neural networks. Today we'll be talking about how to train a neural network. As a review, let's start with forward propagation. So this is just how data flows through the neural network, what the composition looks like if we draw it out in a diagram. So here we have a training observation which we might call xi, yi. The input -1.1, 0.6, 0.1, -0.3 maps to the output -2. And ideally, we'd like the neural network to align with that, to approximately reproduce that result. And the values that we get to adjust are the weights, which are indicated here in green and gold. So the thickness represents the absolute value of that weight, and the color represents the sign. So here we have our first map, which is W1 times X plus B1. And then within each pill, we have our activation, which in this case is ReLU, which means that positive numbers are returned as is and negative numbers are mapped to 0. Then we have another affine map, A2 of X equals W2X plus B2, and so on. In our very last layer, we just have a single neuron, and that's the output of the network. So in the picture, we're showing the entries of the W's with these edges, but we're not really showing the biases. If we wanted to show the biases, we would need to add something sort of to the left of each pill, showing how the weights that come in after multiplying the values coming out of the previous layer add together and then also add to the bias value. So what we'd like to do is measure the difference between the observed output yi and the value actually output by the neural network, which in this case is 0.8. So we apply some sort of loss function, such as just the squared error, and compute that value here. And the goal is going to be to adjust these values we have control over, all of these W's and B's, to make this loss value go down. And not just this particular loss value, but the loss values for all the observations in the training set. Or at least on average, the loss across all observations should go down. So let's see what that looks like dynamically. If we adjust this weight, see it's this top weight in the first layer. If we adjust that weight, it changes the values through the network. So you see them changing much more rapidly in the right picture, and that's because there's a -1.1 value for the component that multiplies that weight. So if we give too large of a weight here, we end up with a negative coming into the ReLU, which gets eliminated. And through this range of values, as we adjust the slider, nothing changes subsequently in the network. However, once we get past that threshold where we're getting zeros, we do change the values. So the loss goes up or down depending on how we're making these adjustments. And likewise over here, the values are changing as well, but they change more slowly because this weight is multiplying a 0.1 to contribute its term in this neuron. So there's some tension in this diagram for these two training observations. Depending on how we adjust the slider, we might increase this loss while decreasing this loss at the same time. So what we're going to do is just work out a recommendation for each training observation that says, okay, for this weight, given its current value, if I adjust it down a little bit, how does the loss change? If I adjust it up a little bit, how does the loss change? And the recommendation for each training observation is going to depend on how rapidly the loss changes at that value. So if our parameter happened to start up here, the pre-activation value here is negative, so as we adjust the weight a little bit, nothing changes. So the recommendation will just be 0. But over here, the loss is going down as we decrease the slider slightly, which means that the recommendation for this training observation is going to suggest going down a little bit. And this idea of how much does the output change when we change the input by a little bit up or down, that's exactly the notion of a derivative. So what we want to do is replace this weight W with whatever it was before minus the derivative of the loss value with respect to W. So in mathematical terms here, the function that we're differentiating is the composition of all the subsequent maps, including the activation function and all of the rest of the maps in the diagram. When we differentiate that full composition, we'll know how much does the loss change when we wiggle W a little bit. Then we'll move in the opposite direction because we want the loss to go down, and we'll scale it by a factor of epsilon called the learning rate. So this is just avoiding taking too big steps in the direction we choose to go. And the way a single update will work is we're going to take every weight in the diagram, and there are many of them, so everything that's a parameter, including the bias values which aren't shown in the picture. And you want to think of an agent sitting on each one of those edges and thinking to itself, if I adjust my weight, how much does the loss value change? Holding everything else fixed. So that's the way taking a gradient works. Each component considers its own impact, that's called a partial derivative, and every parameter adjusts itself independently of all the other ones on a given update. So if each parameter takes a small step in a direction that makes the loss go down, then as long as the step is not too big, hopefully the loss will go down as rapidly as possible. So just as a reminder from multivariable calculus, the direction of the gradient is the direction of maximum increase. If we're adjusting each of these parameters in proportion to the partial derivative of the loss with respect to that parameter, then in total, the full collection of parameters is going to be inducing the most rapid possible decrease in loss instantaneously at that point. And just as a further reminder, the reason that that result holds is that the directional derivative of f in the u direction, where u is a unit vector, is equal to the dot product of the gradient with u. So that comes from linearizing the function f. And that's telling you that the directional derivative is the norm of the gradient of f times the cosine of the angle between u and the gradient. And since cosine is maximized when theta equals 0, that means that the direction u, along which the instantaneous rate of increase for f is as large as possible, occurs in the direction of the gradient. So the correspondence here between this general discussion and the neural networks is that the function f represents loss and the x's represent the parameter values, all the w's and b's. So let's look at this from a different perspective for a smaller neural network. We're going to do it symbolically. And the punchline here is going to be that this is not the right way to do it. We'll discover a better way, but along the way, we'll get another look at this differentiation story for how we're training these neural networks. So what we're going to do is just give ourselves a variable for each of the weights and biases. So we have A through I here. And ABCD is the weight matrix for the first layer, EF is the bias vector for the first layer, GH is the weight matrix for the second layer, and I is the bias for the second layer. So we begin by defining our variables and then setting up an ordered dictionary for the specific values we have at the moment. So symbolically, if you want to differentiate, this is how you have to do it. You have to represent the value you want to differentiate with respect to as a variable, and then you have to substitute after the derivative is taken. If you substitute the value for the variable initially, you can't take a derivative anymore. So that's a basic fact from calculus, and it's going to be relevant for how we're coding this example up. So this was the example from last time. We have this function x plus y squared, and we're trying to see if we can get a neural network to do something like that. And we started with some random values of the parameters, and it looks like this, which is not particularly good, and we want to try to improve it. So first of all, we're going to put ourselves in a slightly more realistic setting data-wise by representing this function not with the actual expression for the function, but a pair of input-output values, where the inputs we've chosen just randomly from the unit square, and the output values are actually computed from the regression function with some additional noise. And we want to say to the neural network, here we have these training observations, and work out how far you are from the correct y value, and coordinate the adjustments to all the parameters in the network, A through I, to try to get better outputs, to try to reduce the loss. So we're going to define the ReLU function as a SymPy piecewise. And we have to use this strange greater than sign and less than or equal to sign, because that's how the sympy.jl package is set up to handle inequalities with variables. In our neural network, since it's quite simple here, we can just write out explicitly. We do w1x plus b1, then we do a component-wise ReLU, and then we multiply that by w2 and add b2. And then we'll just write this function substitute to simplify the process of substituting our actual values in. So if you recall, theta is going to be a dictionary storing our current parameter values. So if we let little x be the first row of x, that's an example of a training observation. And then y of 1 is the corresponding response, 1.73 in this case. So what we want to do is take these two values and come up with a squared error. So that's just going to be y1 minus n of little x. And we need to include these other parameters in the function n and then square all that. So what we get for this particular observation is this piecewise function. You'll see we get some contributions of 0 for where the ReLU is eliminating the value coming in, and we get some, in this case, quadratic combinations of the parameters otherwise. So this first term will have an a times an e in it, and then also an e times a b, and so on. So remember, these parameters correspond to the weights and biases in the original diagram. ABCD correspond to these 4 red lines, GH corresponds to these. So this expression we can differentiate now with SymPy because we have variables in here, and SymPy knows how to differentiate piecewise functions and certainly quadratic functions. So this is something we can do. However, we do want to include other observations. So this is just for a single observation, and if we did gradient descent on this one, we would produce a perfect output for that particular training observation, but probably wouldn't be good for other ones. So the first way we're going to modify this is we're going to loop over the rows of x and y. and we'll just take the mean. And then we'll substitute our actual parameter values to get specific numbers rather than just a very large algebraic expression. So in this case, our average squared error is 16.4. What I actually want to do in this case is leave the substitute out of it for now so that we can reuse this function here and still be able to differentiate. So in part B, we want to just take this expression and differentiate with respect to each parameter in theta. That does require that we not substitute initially. And actually, since we took the substitution out, we can take theta out as well. So we'll take MSE that generates a big algebraic expression telling us what the mean squared error is. And then we just want to differentiate that with respect to each parameter. And then we'll want to substitute. So once we've differentiated, we can perform a substitution and we'll know what the derivatives are at the particular parameter values we're currently at. So we get these values, and remember, partial derivatives are telling us if I adjust this particular component by a very small amount, then I can multiply that amount by this value that I'm seeing for that component, and the resulting change in loss should be approximately that product. So for example, if we make a new set of parameters, which we'll build by copying the old one, so this is an ordered dictionary mapping variable values to numerical values. And if we take, let's say, A and increment it by 0.01, then we can plug in those new values to the mean squared error and also plug in the original values to the mean squared error. And the change that we should get, so this is coming from incrementing the A value from 3 to 3.01, it should correspond to the product of the change, which is 0.01, and this value 3.28. And that's indeed what we get. So it's off slightly because the derivative statement is really only true instantaneously. So for a positive number like 0.01, it's going to be slightly off typically. But it is very close. We can see that if we had wanted to change the loss by this amount, increasing A by 0.01 would have done it. And likewise for each of the other parameters. And what you can see from this vector is that this fifth component has much more influence than the other ones do. Even a very slight change in that parameter will produce quite a large change in the loss. So again, what we'll do in the training process is we'll take A through I and we'll adjust each of those parameter values by negative epsilon times this component that we see, based on the current parameter values that we have. Then, based on those new parameter values, we'll compute new derivatives, multiply that new gradient by negative epsilon, and take another step. And we'll repeatedly take steps in this way, and hopefully, because we're moving in the direction of maximum increase locally, if we take relatively small steps, we're going to move down towards some sort of at least local minimum. And when I was building this exercise, that was my intention at this stage, to see how this update works. But it doesn't really work, actually. And the reason is that the updates are just too slow. We do need to take quite small training steps in this case to avoid the parameter values going way off in a bad direction. And when our updates are very slow, it just takes a very, very long time to start seeing the parameters converging to a good set of values. And the core issue here is that these derivatives are being taken symbolically. We want to improve on that by never representing any of the parameter values as actual variables, as in SymPy variables, but instead represent them as numbers and come up with an efficient way of computing all the derivatives directly in that context. But before we get into that, I want to go to the TensorFlow playground first. So this is an in-browser app that actually does neural network training in your browser. So we have some questions here to guide our experimentation with this tool. First one says, about how many epochs does it take for the network to discover the radial structure of the data set? So we have this data set. We're just giving it the original input features, the x value and the y value. And we have 3 neurons in this hidden layer. We're using sigmoid activation and a learning rate of 0.03. And if we start training it, what we'll see is that it discovers the radial structure fairly quickly, about here, let's say. So this is about 359 epochs in. And this term epoch, it just means number of passes through the data set. So here we're using a batch size of 10, which means that for each gradient update, we're just getting 10 training observations to weigh in. So we randomly choose 10 training observations. We compute the average loss for those 10 observations, and then we compute the suggested updates to each parameter based on that. So the derivatives of the loss with respect to each parameter, and then we make a step. So the steps here are going to be random. They're going to depend on which set of 10 training observations we got. And I believe there are 100 training observations here in total. And with a batch size of 10, that means you're going to get 10 updates per epoch. So an epoch, again, is just one pass through the data. So if you have 100 observations and you're only using 10 of them at a time, then you make one pass through the data for every 10 steps. And the trade-off here is that if you use a larger batch size, you're having more votes contribute to your parameter updates. And so the updates might be a little smarter, they might be in a better direction. but it takes more compute time to do each update. So within a given amount of time, you're not going to be able to take as many steps. There's a trade-off here between small batch size with sort of very quick sloppy steps and larger batch size with more measured steps that take longer to take. So in any case, we get through about 350 epochs, so that's 3,500 training steps. So you can tell already this is just drastically faster than what we were experiencing with SymPy trying to do symbolic derivatives. And indeed, under the hood here, the code is not doing any sort of symbolic computation. If we drop down to 2 neurons in the hidden layer, then what we find is that the model doesn't really have enough expressivity to discover the radial structure of the data set. It ends up doing the best it can with the ability to essentially just make a V-cut like this. And of course, it ends up misclassifying all of these points on the right side. However, if we apply an initial map here between the input and the first layer, by also computing the squares of the features, then it can very quickly discover the radial structure of the data set. And that's because x1 squared plus x2 squared is r squared, which is the variable that you need to split on to separate green from blue in this case. So the key idea for computing derivatives of the loss value with respect to each parameter in a neural network is the chain rule. So the chain rule, if you recall from single variable calculus, just says that if you're composing functions and you want to know the derivative of the composition, you can get that by just looking at the derivatives of each function individually. The idea is that we're taking the original curvy functions and we're linearizing them, we're flattening them into a straight line. And if you were to compose these two straight lines, then the composition would have as its slope the product of the two original slopes. So for example, with the squaring function and the sine function, we have this steep positive slope at the value x equals 2, and then at the output value of that, 4, we look at the corresponding position on the sine graph, and we get this shallow negative slope. And if you multiply a large positive number with a negative number that's between -1 and 0, it's going to be a negative number, and it's going to have a slightly shallower slope. So the steepness goes down from here to here. So these diagrams we've been drawing for these neural networks are examples of something called a computational graph. And a computational graph is just showing how functions are composing together to give an output. So in the simplest case, you have an input coming in on this side. The sequence of compositions is represented with a sequence of arrows, and the blocks in between indicating the output of the previous map is going to go into the next map. And then at the end, we get the computational graph's output. A more complex computational graph might have other things going on, like maybe a separate chain that feeds into this one in various ways. But for now, we'll just consider this simple chain. And the point of the chain rule is that it says if you have each map representing a single step here, and you want to compute derivatives between two nodes of the computational graph, you just multiply corresponding derivatives. So we can differentiate f, differentiate g, and differentiate h, and just multiply corresponding derivatives. So if we want to know the derivative of the output with respect to, let's say, this node, we would just multiply these two matrices. Well, if we want to know the derivative of the output with respect to the input, we would multiply all three matrices. So again, the chain rule is just telling you in a computational graph, replace each basic function with its derivative, and then you can just multiply derivatives instead of composing functions. And that gives you the derivatives of the compositions. So in problem 3, we're going to do that for this neural network computational graph. And the basic parts are the cost function, which maps the output together with the desired output, which is a constant, to the actual cost value, as well as these activation functions, which apply the activation to each component, as well as these linear maps A1, A2, and A3. And the linear maps are going to be no big deal. They're already linear, so to differentiate them, we're just going to get the matrix W corresponding to that linear map. The Ks are also not terribly complicated because they only act component by component. So we'll have to think for a second how to write that down. But that also won't be really hard work. And then the CI function is also something we've seen before. So let's work out these three types of steps. So we want to differentiate the difference between y and yi squared, which is the same as differentiating y minus yi transpose times y minus yi. And then we can apply the product rule. We get the first vector transpose times the derivative of the second vector. And the derivative of the identity times y is just the identity. And then we can do that again for the second term, but we're actually going to get the same thing. We've seen this a few times because of the symmetry between the two terms. So we can just put a 2 here. So the output k dot of x is a vector, and x here is a vector. So when you differentiate a 1D array by a 1D array, you're going to get a 2D array. So the ijth component of this derivative should be the derivative of the ith component of k dot of x with respect to the jth component of x. And from that, we can see that all the off-diagonal entries should be 0, because like the derivative of k of x3 with respect to x5 is just 0. The two variables have nothing to do with each other, so the derivative is 0. On the diagonal, we can get values that are non-zero. And we'll just leave this general by saying, let's say the derivative of k of x1 with respect to x1 is just k dot of x1. So k dot is just the derivative of k with respect to x1. And we'll write the derivative with a dot over the top of k. We want to avoid using primes because we're using those for transposes. And in physics, you often have derivatives indicated with dots. And we can introduce another piece of notation to kind of shorten this, which is the function diag, which just takes a vector and puts that vector on the diagonal of a matrix whose other entries are 0. So this maybe looks a little bit weird, but this dot is the derivative. This dot means we're still applying that derivative function pointwise to k. And then diag means we're taking that resulting vector and turning it into a diagonal matrix with those components along the diagonal. Finally, as we've seen, the derivative with respect to u of wu plus b is just w. It's just like the derivative of 7x minus 2 is 7, derivative of wx plus b is w. So that's going to be enough for us to get started on implementing a neural network in code. So there are lots of ways to set this up, and this is just one. It's not as general as it could be, but it's perfectly reasonable for pedagogical purposes, and it will perform well. So we're going to start by giving ourselves an affine map struct, which represents an affine map in the picture, one of these A's. And it's going to consist of a matrix W and a vector B. And a neural network will consist of a sequence of those affine maps, so a vector of affine maps, as well as an activation function. And just because the function is so easy to differentiate in this case, we're going to have the user differentiate it and supply that information as well. So we need to say how an affine map acts as a function. If you try to call an affine map on something, what should it do? And it's just saying wx plus b. And then for the neural network, the way it takes an input and produces an output is something called forward propagation. So we're going to have to write this function, but once we write the forward propagation function, which goes through and computes the values in each of these nodes left to right in the picture, we can just take the last one. That's going to be our output. And this works because when we define the function, we're not asking Julia to go look up forward prop and do something with it. We're just telling it, this is how this function should work. So as long as we define the forward prop function before we try to call it, everything's going to be fine. And finally, the architecture is just extracting the lengths of these vectors as you go along. So in this case, 3, 2, 4, 2. So let's define the neural network that we were studying at the end of class last time. We'll see how well this manages to fit the data. So these are the W's and B's, and then we were going to use ReLU activation. The derivative of the ReLU function is just 0 along the negatives because it's returning 0 throughout that region, and 1 on the positives because it's returning the identity function on the positive reals. So we set up a neural net with these affine maps and this specified k and k dot, and we're going to call it NN. That's our neural net. So we're asked to complete this forward propagation function. So activations is a common name to give to the values that are coming out of a neuron or out of a layer of neurons. And we'll start with an activation vector, which is just the original input. And what we're going to do is grow that vector of activation vectors. So we're going to loop through the maps. Enumerator is an iterator that assigns to this first variable the index of the step. So it starts with j equals 1, then j equals 2, and so on. And the second variable is assigned to the corresponding entry of this list. So this is equivalent to zipping the range from 1 to the length of n maps with n maps. Okay, so we're gonna push to our activations vector a new vector, which is just what we get when we apply the affine map. So our latest computed activation is accessible at the end of that vector. And then we apply a to it, and we've told Julia how this affine map a should act when we treat it as a function. And we're going to tack that on to the activations. And then we need to apply k and keep track of that as well. So we're going to say, let's use the k function associated with the neural net and map that over the components of the last vector we computed. Except that's not quite right, because the very last activation is the identity. If you recall in this picture, we use k dot for the first 2 layers, but then when we get to this third affine map output, we actually just leave it alone. So this is called linear activation. It's just another term for identity activation. So we need to work that in somehow. And one kind of easy way to do it is just check whether j isn't at the end yet. And if it's not, then we'll use k. And if it is, then we'll use the identity map. So identity is a built-in Julia function. And then we have this test. We're going to see if we put in -2, -3, then our first vector should be the actual input we started with. Then the result of applying the first affine map. So if you do w1 times -2 -3 plus b1, you should get this value. Then the ReLU is going to hit that and wipe out that -12. And then the second map turns out to output just a vector containing a single number of 7. And then these last two are always going to be the same because we're applying the identity there. So this is what should happen, and we're checking that that's the case. And it looks good. If we wanted to see the result of that test, we'd leave that on the last line. It'll say test passed. So at least for this little example, our forward propagation function did the right thing. Now we want to compute actual derivatives. And here, it's worth reflecting for a moment before we get into that on what it is we're trying to do. For now, what we're trying to do is for each vector component in this primary chain of the neural network, so neglecting this part for a minute. If we manage to induce a small change to this value, let's say -5, how does that change the resulting cost? In other words, we're trying to compute the derivative of this composition. And the chain rule says we just differentiate these pieces and multiply, so that part is fine. But bear in mind, we're trying to do this for every parameter. So for this vector, we're differentiating this composition. For this vector, we're differentiating this whole composition. For this vector, we're differentiating this composition, and so on. So if you imagine we did this in the kind of straightforward way of starting here and then multiplying all the derivatives to the end of the line, and then once we have that, we move over and multiply all the derivatives from the next point to the end. We're computing a lot of the same products. It would have been better if we had this one already, and then we could just tack on this one additional derivative to get one step to the left. So what we actually want to do is start with this very first map, compute this derivative, and then compute the derivative just before it by just multiplying one additional derivative, and then computing the derivative just before that by multiplying one additional derivative, and so on. And this process has a name. It's called backpropagation. So rather than just giving this whole computation to a system and saying compute these derivatives, we keep track of the derivatives we've used so far and use that to save computation time. So if we have n layers, we just have to do n multiplications, like 1, 2, 3, 4, and so on up to n. Whereas if we try to do this from the beginning, we would have to do n multiplications to take the derivative of the cost with respect to this first vector, and then n minus 1 more multiplications for this second one, and so on. And the sum of the first n integers is n times n plus 1 over 2, and that's quadratic. That's the order of n squared. So that's the benefit of doing backpropagation rather than computing gradients forward. It comes from the fact that the gradients we need are all between this end node and some node at an earlier point in the chain. So let's do it. Let's start our list of gradients with the derivative of the last function, which is the cost function, which we decided is 2 times y minus yi transpose. And then for each map, we'll just walk back through the diagram. So we have our layers enumerated, j equals 1, j equals 2, and j equals 3. And for each one, we'll just account for the activation we used, and then this affine map, and then loop through all the way back to the beginning. So for the activation, what we'll do is compute the diagonal matrix with the activation derivative k dot mapped over the vector of values coming into that function k. So if we're talking about the jth map, then the values coming into the activation are in the jth purple node. And we have a function purple node which tells us the index of the jth purple node in the full list of activations computed during forward propagation. So the jth purple node, we extract that activation, we map k dot over it, form a diagonal matrix. That's the gradient of that step. Then we need to multiply that by the last gradient we had computed because we're working from right to left across the diagram. And grad's end is going to represent the running product from where we are now to the end. And notice that the new multiplication happens on the right rather than on the left. That's because that's how function composition works. Data flows through the diagram from left to right, but when we apply functions, we apply the one on the right first. This is hitting the input first, so it needs to come on the right. And then we just push that on our list of gradients. Next, we account for the affine map. And that one's easier because the derivative of the affine map is just the W matrix associated with that map. So we look at the jth map of n, and we extract W, and then we multiply it on the right by our current running product of derivatives. And that's pretty much it, except if j is equal to the length of n maps, we're looking at the end. Remember that we are not using an activation there, or rather we're using the identity activation. So what we want to do is multiply on the right by the identity matrix. In other words, just do nothing. And only if j is less than the length of n maps are we actually computing this k dot thing. So again, that's because this is the identity and these are actual k's. So we get a list of adjoint matrices, list of row matrices. And that makes sense because they represent the derivative of a scalar with respect to a vector. Now we finally have to deal with the fact that we're not able to control these components directly. We're only able to control the w's and b's. So we have to see how they hook into this derivative story. And the biases are not so tricky. For example, a2 of x is w2x plus b2. So if we change b2, it directly induces a corresponding change in the corresponding component of the vector in that purple node. So if we know how a change in that component affects the cost, a change in b affects the cost in exactly the same way. In other words, the derivative of this step coming down from that bias vector to the purple vector is just a derivative of a2 with respect to b2, which is just the identity. However, we also need to deal with the weights. In other words, we need to differentiate, let's say, a2 with respect to w2. And this is a pretty interesting object because the output of a2 is a vector. It's this purple vector here. But w2 is a matrix. We have a 1D array being differentiated with respect to a 2D array, and that's going to give a 3-dimensional array. So we can say this is a rank 3 tensor, meaning that it's like a matrix but 1 dimension up. So if you want to visualize this, it's like a rectangular prism of values. And that's pretty challenging to deal with algebraically, but if you think about how it's going to be used here, the thing we're going to need to do with it is multiply by the gradient we have sitting at this purple node to get from the purple node up to this blue one. And that gradient is a row vector. So really what we need to know about this rank 3 tensor is nothing other than how does it multiply by a row vector. So this is what we're trying to understand, how to differentiate wx plus b with respect to w. And what we want to do is say, suppose that u prime is a row vector. How does that multiply by this derivative? Without having to think too hard about how to give this derivative meaning, surely it should be linear, in which case we should be able to pass the u prime inside. So that just corresponds to taking the components of u prime and passing them inside that derivative operator. And now we're in a much more sensible place because now this is just a number. And we can think about differentiating a number with respect to a matrix to get a matrix just by differentiating each component one by one. So first of all, this b term doesn't involve w. So we'll use linearity again to get rid of that. And we decided what this should mean is the derivative of uwx with respect to wij, the ijth component. And we're going to let I comma j range over the indices of w. That'll give us a matrix, and that's going to be what we mean when we say the derivative of a scalar with respect to a matrix. And if you multiply this product out, what you'll see is that the wij term only involves ui and xj. And in fact, that term is just ui xj times wij. So this derivative is going to be 0 for every term other than that one, ui xj. And so we get a matrix whose ijth entry is the product of the ith entry of u and the jth entry of x. And this is the same thing as the outer product of u and x. In other words, just u x transpose. So that's the key idea, this extra thing that we get to step up from a given purple node to the w that feeds into it, multiplies by a row vector to produce this result. So that's what we have programmed here. For the bias gradients, we just directly pull out the gradient for the corresponding purple node. And for the weight gradient, we compute this u times x transpose value. Next, we'll do the work of averaging the suggested changes coming from each observation in a given batch. So we start with 0 matrices for the suggested changes, and then we loop over the batch, and for each x comma y pair in that batch, we forward propagate and then back propagate to compute all the gradients. And then we say, okay, for what are our weight gradients? What are the suggested changes to the weights? We'll keep up with those in a list called delta w's. And what are our bias gradients? What are the suggested changes to the biases? We'll keep up with those in a list called delta b's. And we just go through and add the suggested changes to this matrix, keeping a running total of the suggested changes for that weight matrix, and the same for the biases. And then finally, at the end, we take those sums and divide them by how many observations we were looking at. Lastly, we'll define a function which trains a neural network by starting out with random weights and biases. Actually, the biases are just 0.1. The weights are random though. We form a neural network with those random maps and the given activation function k with its derivative k dot. And then for each I from 1 to iterations, we're going to form a batch, and that batch is just going to be a sample of observations. So we'll do this index-wise. We'll sample 1 to length observations, and the sample size is going to be batch size. So that's an argument to the train function. And then the average suggested change in the weights and the average suggested change in the biases is going to be computed with this average weight change function we wrote. And then we need to update our neural network. So we make a new neural net consisting of a list of affine maps. We need to know what's the proposed change in W, what's the proposed change in B, and then we also need to know the original map in the neural network we started with, and then we actually apply the suggested change. So we'll come up with our observations here, and then we'll train our neural network. And then we'll plot our neural network and compare it to the target function, and we'll see that it did a very nice job of aligning well with the actual regression function given the constraints of the architecture. So in summary, to train a neural network, we take a collection of training observations which consists of input-output pairs. And for each observation, we run the input forward through the network. Then we differentiate each function mapping one node to the next and multiply them progressively from the back to calculate the derivative of the cost, which measures the discrepancy between the output and the desired output, and each node in the diagram. And then lastly, we adjust the weights and biases according to the computed gradients. And to do that, we just need to be able to take derivatives of each map in the figure. For example, the derivative of the cost function, assuming we're talking about mean squared error, is 2y minus yi transpose. The derivative of the function that applies activation component-wise is a diagonal matrix whose diagonal entries are the derivatives of the activation function applied to each component of the input vector. The derivative of each affine map is just the corresponding weight matrix. And for these vertical segments, the derivative with respect to B is just the identity matrix. And the derivative with respect to W is a rank 3 tensor, which is characterized by the property that if you multiply it on the left by a row vector, what you get is the outer product of that row vector with the vector x. Finally, the set of input-output pairs we consider for a given weight and bias update is called a mini-batch. Typically, for performance reasons, we won't use all of the observations in a given update. We'll just use a few of them, and then we'll cycle through the data set so that over time all of the observations are accounted for.